would need private data for both training and inference. But if you want to leverage existing innovation and investments which have been made on, let's say, large language models, then potentially you would want just to fine-tune those models using your enterprise data. And here again, the reliance on private data is still exists. Having said that, when we look at the AI landscape, we know that a lot of enterprises are interested in deploying AI that specifically answers their use cases. A lot of organizations, as much as 96% of them, are today in a pilot stage for AI initiatives. And to make those successful, the need for data will come up. However, the interesting statistic to share here is in the medical field, for example, 80% of data is not utilized at all. So this is quite a paradox. We're saying these people are investing in AI. They do require large amounts of data to make their initiatives successful, and yet they are sitting on this much unutilized data. So what's happening here? By the way, the statistic here for the medical sector, but the same goes for all other industries. There are a lot of things which are making such large amounts of data to go unutilized. Some of them might be the fact that knowledge is still being built up within those organizations. Maybe the data is unstructured and is more difficult to work with. But one of the main challenges which are hindering the successful adoption of AI in the enterprise are security concerns, really. The security concerns reflect the fact that we have a lot of security-sensitive data that needs to be fed to AI models. And in a lot of industries, it's not just the fact or the genuine worry about the fact that this confidential or security-sensitive data might be compromised. It's just that by regulation, you cannot make use of it in certain, let's say, public cloud deployments, or you cannot feed it to a public AI model. So there are constraints which you have to deal with in order to utilize your private enterprise data. Another pillar which has been which has made AI successful is access to a lot of compute. So the enterprises are looking now to replicate the success of the likes of ChatGPT by also looking for ways to find a lot of compute power. And one way to make that happen is to leverage the public cloud. And this brings us back again to the security challenges that AI faces. The public clouds, as greatly managed as they are, they do have security vulnerabilities. Actually, as much as 45% of all data breaches reported are related to cloud-based deployments. This is besides the fact that we are now talking about some sort of sensitive regulated data having to live in a public cloud infrastructure, and that's not always okay. Sometimes that data, you would prefer that that data lives in your private data center unless you have some further security guarantees from the public cloud provider. And this is what we're going exactly to tackle in this webinar today. So there is a security challenge, that's undeniable. And we have to be very detailed oriented. We have to be very specific when trying to solve security. So let's do exactly that for the rest of this presentation. What are we trying to protect? Well, actually, we need to protect both the data and the model. We have explored why protecting data is necessary, but the model in many instances is considered IP. An IP that an organization might have spent a lot of effort to come up with, and it wants to protect it from just being used by competitors or just others. So it's intellectual property. Okay, now we know what we want to protect, but who do we want to protect it from? In another way, what is our attacker model? This is a fundamental question to any security exercise. And to answer it precisely, well, let's go. First of all, I know I need to protect it from something that might go wrong in the computing platform on which the AI is going to be trained on, and also on which we're going to perform inference on. So let's have a look at those computing platforms. At a high level, all of them, regardless of the architecture, they follow this concept of abstraction layers. Computers have been designed since the beginning around this very powerful idea in which every layer will be performing a set of services and giving them for consumption to a layer that is underneath it. So what we are mostly familiar with here would be, for example, the kernel. The kernel is privileged system software, and it provides services to the application layer. Your AI model is going to be deployed in the application layer in ring 3 if we are talking about x86 architectures. This is great because the kernel effectively will be responsible from hiding away from you as an application AI developer a lot of the complexity of how you will manage memory, how will you allocate memory pages to your application. You don't have to worry about that. You don't have to worry about how to access a certain IO device because the drivers take care of that for you. So abstraction is a great concept, and it's truly what has helped us come up with so much innovation in the computing ecosystem. However, for so long, actually since the beginning of computing, we have accepted that if my data is going to be managed by some system privileged software, if the kernel, for example, is going to be responsible for taking my, I don't know, password and allocating it to a certain memory page, we've accepted then, well, of course, it's going to have access to that data. I mean, otherwise, how would it be able to manage my data? So this implication here has been just how computing works. It wasn't a bug. But if you really just take a moment to think about the security implications of this, and we ask ourselves the question of what could go wrong with these millions lines of code of privileged system software, because effectively, everything, we're not talking about a small software stack, all the way up from system management mode to the hypervisor, the kernel, the guest OS, and the drivers. These are millions lines of code, and they just keep on growing in complexity every day. So what can really go wrong with this huge software stack? Well, apparently a lot. We're going to start light. Any piece of this privileged system software that controls your data and code can be benign but vulnerable. So it means that maybe some developer along the line has made a mistake, and then, I don't know, a buffer overflow was introduced in the kernel, and now we have a vulnerability. We know this is very, very common occurrence. Vulnerabilities across the stack are common. That's why we have CVEs which describe vulnerabilities, and that's why actually at Canonical we offer patching of these CVEs for, well, a lot of pieces of the stack. So this is not unusual to assume that the software, the privileged system software, is going to be vulnerable. And once it is vulnerable, well, by definition, it will compromise it might compromise the security of your AI model and its data if somebody leverages or exploits the vulnerability. However, that's not the only thing that can go wrong with the computing infrastructure you deploy your AI model on. Besides being vulnerable, it can also be malicious. So what does that mean? It means that let's take the perfect assumption. There are no vulnerabilities. All the developers have done their job properly. There is no CVE to patch, but still the operator of the infrastructure can just decide to take your data and hand it over to whomever is going to knock on their door. So they might have a subpoena from some governmental entity, and they can decide to leak it to them. So that's the malicious part of what can go wrong with the privileged system software. This brings us to what I find to be a very obvious requirement that we should all strive towards, which is we want to protect our application, which in this case is your AI model and its data, from the host itself. So the host, meaning all of the privileged system software that sits underneath your application, as well as the administrators of that particular platform. So here I'm going to ask some questions in order to show that actually this is an unsolved problem. We've just been doing computing assuming that whatever, like if we have a vulnerability in any part of the host, then of course I should accept that it can compromise my application. And some of the questions when I speak about this as a gap is, well, what about me running my application in a container, maybe even in a VM, which has stronger isolation guarantees? Well, that's good. But containers and VM, they provide security of the host from your application. So it's the other way of the equation that it satisfies. What you want is to protect yourself from the host the same way that the host protects itself from you. And it makes even more sense for you to require this level of security because the host is the more privileged party in this equation. Well, another question would be, is it not enough that I encrypt my data at rest? So it is, when it is perhaps sitting in disk, I'm encrypting it. So that should protect me from a malicious and vulnerable kernel, for example. It does not. That's a simple answer. It does not, because when your data is sitting encrypted in secondary memory at storage time, that's good. It will be safe as long as it remains in that state. It just sits idly in storage. The moment you want to do any sort of compute, the moment you want really to derive any sort of value from your data, you have to bring it into system memory from secondary memory. You have to bring it from disk into RAM, for example, and you have to decrypt it. You have to decrypt it to do any sort of computation on it. And once that happens, the privileged system software, the host that you're trying to protect yourself from, is going to have unlimited access to both your code and your data. And this is just how computing works. I'm not disclosing here any vulnerabilities. This is really just the state of computing. So those questions that I mentioned, what about a VM, or what about encryption at rest, are legitimate questions, and they do serve a purpose. So for example, storage security, it solves the problem of securing data at rest when it's sitting idly. When you are trying to send data, for example, from your machine to a public cloud server, then we trust that you are going to make use of secure transport protocols, HTTPS, for example, and that would safeguard your data and your application when it is going over the network. However, I want to highlight here that the problem or the gap we have that confidential computing is addressing is the problem of securing data in use when it is being processed, when it is being computed on by the CPU, and when it is residing in system memory. I've been referring throughout this whole presentation to the public cloud as the potential host that I want to protect myself from. And there are still questions which might come up. What about I just never use the public cloud and I keep my AI and all my applications that have security sensitive data in my private data center? That's not a bad decision. It will give you governance because you will be the one deciding about where you want those data centers to be, in which geographical area. You will be deciding on the insiders, who you're going to hire to be an administrator for that private data center, and that's good. Governance is good, and it might be even required for some industries, but governance does not equal security. The reason being is even inside of the private data center, you are still going to run the same software stack that a public cloud is running. So you're still going to have some sort of hypervisor. You're still going to have a kernel, a host operating system. And those software are subject to the same vulnerabilities that a public cloud host software stack is subject to. Furthermore, insiders are also a threat that you need to mitigate against when you are in a private data center setting. A lot of industries which are in the private data center also have multi-tenancy requirements, the same way that public cloud does, but it's also in a slightly different manner, because the multi-tenants here might be just some different departments within the same large organization, or it might be that, I don't know, a telco company is renting out portion of its infrastructure to, I don't know, a media organization that wants closer infrastructure. So for all those reasons, the private data center, while it brings governance, it still requires us to think about the need to secure and further protect our applications from the host infrastructure. What if you anonymize your data? You probably should. We have learned time and time again that anonymization is definitely not confidentiality, and it's actually very surprising to see how many little queries you require in order to completely break the anonymization of a data set. It's surprisingly low. So for all those reasons, and I hope I have by now motivated the problem, and we all are looking forward to understanding what the potential solution might be. I'm going to recap. We want to close the gap of data insecurity at runtime. And I'm saying that I don't really trust the execution environment in which my AI application would be operating within. So one very intuitive idea really is to decide that you want to run your security-sensitive applications in an isolated execution environment. So I want to run it in isolation from all these potentially vulnerable kernels and hypervisors and whatnot. But that's not enough, because I might be operating in a remote infrastructure. Maybe I am in a public cloud setting. So I want to have guarantees, verifiability. I want to verify remotely that I am indeed executing my application in that isolated environment. So these are the two main primitives of confidential computing. And like all good ideas in computing, they have their roots in, we didn't just come up with them today. This is such a good idea with that of isolation that we have been making use of it in some form since a long time ago. So you would be familiar with, most of you are familiar with SIM cards. So SIM cards, actually, they are execution environments with processing, storage capabilities. And in Norway, where I live, the banks here, they require some sort of multi-factor authentication. So I need to confirm a transaction when I make it. And it's like, yes, it's me really transferring such and such amounts of money to this bank account. I need to confirm it on my mobile phone. And while the mobile phone is where I look at the notification, I confirm it, the applet or the application of the authentication itself that is provided by the telcos does not run on the CPU of the mobile phone. It runs separately in isolation in the SIM card. Trusted platform modules, TPMs, and secure elements are other technologies which have built on this idea of security through isolation. What was missing from these technologies is that when we're talking about a SIM card or a secure element, this is a very low computational power, clearly not by any means enough for AI deployments. So the innovation that confidential computing brings is that it brings a strong level of isolation, almost similar to that you would get with complete physical isolation, because the SIM card is really completely isolated from the main CPU of the mobile phone. But confidential computing gives you isolation in a logical way, and we're going to see exactly how that's achieved. So the logical part, but what I mean by it is that you run within the same powerful CPU, but you are isolated from from all the host software stack that runs on top of it. I'm going to focus on the second iteration of confidential computing. The first one was focused on just isolating processes, and the technology that made that possible was Intel SGX. The second, not call it generation, it's just a second iteration now with different option, is focusing on actually protecting entire virtual let's say virtual machines for now, and I'm going to tell you why we can have other variants, but entire virtualized execution environment will be available for you to run your AI workload on while leveraging confidential computing. The main two technologies for x86 architecture at least are AMD SNP and Intel TGX. In this picture here, what you see in the green is an SNP, an AMD SNP virtual machine. And then the only other box in green is the AMD hardware and firmware, and everything else, everything that sits between the VM and the hardware is in red. What this means is that if there is a vulnerability today in the hypervisor and your AI model and data is running in a CVSNP VM and not just a normal VM, that vulnerability will not impact your data and code integrity and confidentiality. And that's a very strong security guarantee to have, because effectively what we're saying is, yes, dear host software stack, go on with your vulnerabilities. I am protected, and my security is rooted in the hardware and firmware guarantees of the CPU itself. This strong security guarantee is made possible thanks to architectural extensions to existing hardware-assisted virtualization technologies. So both Intel and AMD have extended VTX and AMDV respectively. And what this has made possible, I mentioned, it can be a full distro full VM, like the normal VMs that we're used to. But it can also be a lightweight VM. It can be a micro VM. You can even have a VM running a container within it. And this is just to signal that, yeah, it's not a size fits all. There are different trade-offs to be made when it comes to performance, portability, and otherwise that would require someone to sit and choose the right way for them to consume confidential computing from either Intel or AMD. Such a strong security guarantee, you can imagine it requires some changes. Luckily, those changes are not required for your application. For you, that will just be a shift and lift experience, literally. But for everything else, for the hypervisor, for the host operating system, for the guest operating system, and for the guest VM firmware, some changes have been required, and there have been a lot of activity in the upstream communities to make those changes, to merge them upstream. And what I'm showcasing here is, let's say you want to build on top of Intel TGX. So what you see on the right side is the guest side. You can have today already an Ubuntu optimized image for Intel TGX. It has patches which are not even available upstream, but we take them in, we test them, and we guarantee their security maintenance and support for the lifetime of the release. And on the host side, we have done the work for you to just take our KVM, KMU libvirt distribution. Basically, all of the pieces are available today for anybody to stand up TDX environments, host and guest, and to just start using confidential VMs with TDX. Even on their private data center, like this is capabilities that public clouds have built themselves. But today, this is possible also for enterprises who choose to deploy the whole thing themselves. So far, I've told you a lot about the security guarantees, and these are strong ones. For the next couple of slides, I want to anchor those in those guarantees in the technical primitives that make them possible. And there are 4 of them. Confidential computing is made possible because of confidentiality, integrity, attestation, and a hardware root of trust. Confidentiality is guaranteed by a new memory encryption engine. It's an AES encryption engine, a hardware encryption engine that sits within the CPU. And what it does is, it is a true work of beautiful engineering, because it has achieved a great performance to be able to be used to encrypt every memory write to the system memory and decrypt every write. So what I'm saying here is that system memory, RAM effectively, will be encrypted. And the memory which is mapped to every virtual machine will be encrypted with a unique encryption key. And the encryption key is stored within a register that no part of the host software stack is able to access. The implications of this are really important to understand, because what we're saying is suddenly the hypervisor might have a vulnerability or it might become malicious. Let's say it wants to leak your VM's data to some malicious third party. It can read that data, that's fine, but all that what it reads will be encrypted ciphertext. So as long as we trust that AES is not broken and the whole internet is built on this assumption, then we're good. We trust that the hypervisor is not going to be able to at least compromise the confidentiality of your AI workload. Confidentiality is great, but it's not enough. Because you can imagine the hypervisor or the host operating system still being able to launch some attacks on the paging, on the integrity of your confidential VM. And the innovation that confidential computing brings is a concept or a data structure, actually, that is called a reverse page map. As the name implies, it does the reverse of what normal page tables do. So this is a structure that is indexed by physical addresses, and it maps back every physical address to the virtual address that the operating system or hypervisor has assigned to it. So effectively, what this gives us, why does it give us integrity, is because the hypervisor can still go on with normal business and be the one responsible for assigning memory pages. But if it decides suddenly to allocate the same memory page to two confidential virtual machines, let's say, so that another one can access your memory, then this data structure will be able to detect and stop that. There will be an abort page. And yeah, that integrity attack will effectively be averted. The third primitive that gives us confidential computing is attestation, because confidentiality and integrity, yes, they give us isolation, but what if the host operator decides to, I don't know, load the backdoor alongside my guest operating system of choice and my AI application? That might happen. So I need some or what if it tells me that it's going to launch my AI application within a confidential VM and then decide, no, I'm going to run it in a VM and just tell that user that it is running this VM. So we are not going to trust the host infrastructure. That's the whole purpose of confidential computing. We want cryptographically verifiable proof that my confidential VM is what I expect it to be. It is running on the hardware I expect, and it has loaded what I expect it to load and nothing more. This is made possible by the attestation, launch time attestation. So as you are launching software into your CVM, there is a hardware root of trust, which is basically hashing the pages of memory which are loaded into the CVM, confidential VM. And once the loading is done, the hashes log will be sent to you, and it will be signed by a key which is rooted into the specific hardware that you are running your confidential VM on. And you should be able to verify two things. You should be able to verify that this is a genuine hardware. You can do that by consulting the verifier, the verification services offered by the Silicon, Intel, and AMD, depending on what you're using. But you should also be able to look at the measurements of the software that has booted and the configuration of the VM and actually say, well, okay, that's really what I expect. I trust this CVM is good. So only then will you be comfortable to release your confidential data to that confidential VM, or even your model. You can choose to abstain from sharing it with the confidential VM until you're comfortable with the guarantees it gives you, if it happens that the model is intellectual property. So that's all great. The Silicon are really the core and the heartbeat of confidential computing innovation. They have done so much to bring this innovation to the Silicon level. And the operating systems such as Ubuntu have done a lot to make it consumable by offering distributions like the Intel TDX, Ubuntu Intel TDX optimized images. We also have all the required bits and pieces for the hypervisor and for the host side. That's good. But are we done? What I've presented so far, what Silicon gives you, is a primitive. It's not a complete solution. We still need to take actually this execution environment, this trusted execution environment, TEE, that the Silicon gives you, and make it a truly meaningful confidential computing solution for your particular use case. So the Silicon primitives, they give us runtime guarantee, and we rely on that. We rely on them for that. Security at rest is still the responsibility of the guest operating system, because you would have to choose an OS for your confidential VM. If you choose Ubuntu, then we offer full disk encryption to still secure your workload when it is sitting idly in storage. You still have to think about how your VM will communicate over the network or with the host. There is this concept of shared memory, and then we're going to see with the GPUs how that's being made use of. And you have to be really a bit sophisticated when it comes to consuming attestation. You have to sit down and look at exactly what the measurements you're getting reflects. And if it's not enough for your use case, you have to think of ways, and I say you have to think. I mean, we do offer with Ubuntu ways to expand the attestation guarantees all the way up to the root file system, but I'm making us aware here of a naive adoption of confidential computing. Just taking the hardware and just calling it a day is not going to cut it. But the solutions are here with Ubuntu for you to make use of and bring the trusted execution environment to a meaningful solution. Another question is, what if actually CPUs are not enough for me? I've been talking for so long about CPUs, but you want to do AI and you want GPUs to do AI, understandably. So great news. NVIDIA is the first and only GPU which offers confidential computing capabilities. This is made possible thanks to the H100, the Hopper H100 GPU. And they work great with confidential VMs. They have to work in collaboration with the confidential VM that runs on the CPU. And this is the high-level visualization of what that might look like. So you will choose an Ubuntu confidential VM, and then at some point you want to do leverage GPU for computation. The communication between your Ubuntu confidential VM and the NVIDIA H100 GPU is encrypted and will be protected from the host, the same way that the confidential VM memory is encrypted from the host. Actually, it is encrypted as far as the host is concerned. And if we zoom a little bit more into what is within the confidential VM, I mean, besides the guest operating system and your application, an important piece here is the NVIDIA driver. So the NVIDIA driver is what makes, or is what takes the responsibility of encrypting and decrypting all the memory transfers to the GPU. So also, actually, I want to highlight here that, okay, let me keep it for another slide. So I've talked so far about how the communication between the confidential VM and the confidential H100 GPU is made secure, it's encrypted. But what about when your data will reach the GPU itself? What makes this H100 different when it's in confidential computing mode? Well, the memory itself, when you have this confidential computing on, is further secured, because you would have hardware firewalls which will refuse access to the GPU memory when in confidential computing mode from access from anything outside of it, including the hypervisor, including the confidential VM, and including from peer GPU, other peer GPU units which might be present on the same platform. The top part of this illustration is what is referred to in the NVIDIA documentation as GPU compute protected region. So you only get this protection if you have confidential computing turned on, but we still need to communicate. I just said that data will be transferred back and forth between the CPU and the GPU. So there is a memory called GPU unprotected memory. And this is actually just basically some bounce buffers in which we put, I mean the GPU will, for example, put encrypted data into the bounce buffer, and then the confidential VM, actually the driver, NVIDIA driver present within the confidential VM will read the encrypted bounce buffer memory and transfer it to the confidential VM, and the reverse would happen when you want to communicate from the CPU to the GPU. So this is a zoomed-in visualization of exactly what are the building blocks of confidential AI with the NVIDIA H100 GPUs and Ubuntu confidential VMs. So perhaps so the detail here is that there is a key exchange protocol which happens between the CPU and the GPU when confidential computing is on. It's a Diffie-Hellman key exchange, which establishes some symmetric keys, and those keys are the ones responsible for encrypting data between the CPU and the GPU. And then the firewalls are what's responsible for protecting your data once it reaches the GPU. I want to make a note here on the performance, given that's a super important metric for AI, is the GPU when in confidential computing mode will perform, it does not have any performance degradation, but as a solution, as a whole, if there are, the bottleneck here would be the transfers between the CPU and the GPU, because some encryption needs to happen, the NVIDIA driver needs to encrypt and then transfer the GPU. So in that regard, you have to do some benchmarking for your application to understand maybe how to better optimize the transfers between the CPU and the GPU. And the NVIDIA H100 gives you the option, besides having on or off the confidential computing mode, it gives you a dev option in which you can have some performance metrics available to you from the GPU. Those would be not available in full confidential computing mode because they can still allow for some side channel attacks to happen, and that's not what we want. So that was about the performance. The use cases, there are honestly many. You can imagine this being super useful in a public cloud deployment on the private data center. And I'm choosing here to talk about federated learning because can imagine a deployment that has a mix of both. So you can still have, it's a federated setting. So each site will have its own local AI training infrastructure, and confidential computing is still relevant in this local setting because it can protect your AI workload from the vulnerabilities we talked about in the hosting infrastructure, from admin access, insider threats, but also it guarantees the integrity of your execution. You are executing exactly what you expect to execute. And once it is time to aggregate, I don't know, the weights from the models, whatever strategy you will choose for your federated learning, the centralized platform on which you're doing the aggregation can definitely benefit from confidential computing in order to preserve both the confidentiality and the integrity of that deployment. Attestation, very important. We've talked about it in the context of the CPU. I want to mention here that it's also available in a very similar way for the GPU. So you would potentially, ideally, get an attestation for the whole CPU, GPU deployment, and you would know that you are operating on what you expect the hardware to be on the GPU and CPU, as well as know that the environments have booted with the configuration that you expect, and that it is only the data that you expect. If this is exciting to you, I'm sure you're wondering, where can you get started on confidential AI? Where can you find us? So on the public cloud, Ubuntu is in preview already for confidential AI with Ubuntu confidential VMs and NVIDIA H100 GPUs on Azure. Please go and try the preview and give us your feedback. We are very happy and consider this a major milestone for our confidential computing journey because we know how important AI for a lot of enterprises today. And we are the only and first OS to support this preview. So please make use of it. If you do not want to experiment with this on the public cloud and you prefer, maybe you have already access to an AMD CVCMP hardware or Intel TGX hardware, NVIDIA H100 on its technical blog, and I have links to this material in the presentation, they have a reference implementation with a recommended software stack. And that software stack, as you can see, refers to the Ubuntu distribution as the preferred operating system. And also the kernel, QEMU, and OVMF. You can take them from our, if you are running this on Intel TGX, we already have those available as well. I've talked so much about how great confidential computing is and how it protects you from, it protects your AI, data and code from everything that sits outside of it. I want to pose another question. Actually, Jehudi is here to answer that question. Is there anything else we need to worry about in order to protect these confidential VMs from themselves? I cannot hear you, Jehudi. Maybe you need to unmute yourself. It should be on the top center of the screen of BrightTalk. No luck. I still cannot hear you.
Is it better?
Yes, you're on.
Okay, I mean a different setup because actually I'm on site right now in Redmond with Microsoft, so different hardware. So answering your question, you have been making a very compelling case about how confidential computing protect your data from external threats. And this even includes the operating system or the hypervisor. But still, we have the issue of the workloads itself. So if you have a vulnerability there coming from a library, for example, that is still an issue. That's why Ubuntu Pro is a very good complement for everyone that is worrying about security. So it goes hand in hand with confidential computing very well. This is an extra add-on that you can include to your Ubuntu, and is free for personal use up to 5 VMs. And on the public clouds, you find it very cheaply on the marketplace. It includes vulnerability management, compliance requirements. These are things like FIPS, that is very important for regulated industries, enterprise management, so your whole fleet you can manage from a centralized place, and you have optional dedicated support also. What it is about, Ubuntu usually offers the infra packages with security updates for 5 years, but with Ubuntu Pro, you have 5 additional years and 10 times more packages. So you also have things like Python, Node, Java, Go, Perl, Ruby, etc., etc. Essentially, all the open source packages that you can install from our repositories have the same security guarantees that you usually have from the operating system. That's what Ubuntu Pro has to offer. So it can help you to have that complement to the CVM. And it's actually very easy to get. If, for instance, you are on Azure, where we just talk about the preview for confidential AI, and you are launching a VM from the CLI, just add this last parameter, license type Ubuntu Pro. Or if you already have a workload on Ubuntu, you can do an in-place upgrade. In that case, it will be a set VM update and changing the license type. This gives that will give you all these extra security updates that we offer.
Excellent. I'm convinced. I mean, it's quite, I believe that if anybody is looking for confidential computing, it's because they are worried about security. They want security in depth. And we have to be mindful about what is within the perimeters of that confidential VM. It gives us protection against what's outside of it, but what's inside of it, with the Pro subscription, you can definitely get that long-term security and enterprise-grade security and maintenance for your AI workload. Where can you find us and learn more about what we will launch in the future? Because we do have a lot more launches coming up. This is our webpage, ubuntu.com/confidential computing. I mentioned that we have made available for everybody a host and guest Intel TGX software stack with setup scripts, which really make it very easy in a couple of commands to stand up a TGX confidential VM. Even for people who want to deploy that on a private data center. So we have a GitHub repository with all the required pieces there. This is it. We have already launched this in preview for Ubuntu 23.10. We are getting very close to releasing our Ubuntu 24.04 long-term supported release in April. And we are going to continue the commitment to making available Intel TGX builds. There is already a dev branch available in this GitHub repo, but as we stabilize it more, we will, you can start building with it comfortably for your production environment. So please do make use of these resources. If you want to experiment with confidential VMs from Ubuntu on the public cloud, then we have the widest offering on all major public cloud providers. If you go, for example, to Azure Marketplace, type Ubuntu confidential VMs, you're gonna get what's we have made available for you there. And that's a lighter way to get your hands on what it is to deploy confidential VMs and deploy AI with this capability, because you do not effectively have to worry about the host side. It's taken care of by the public cloud provider, and you only have to choose what type of operating system you want to run with your VM, which effectively is the same way you would run in a non-confidential VM, a normal VM. If you do have questions, if you have use cases to discuss, either for public or private cloud deployments, we have a contact form. Please reach out. We will make sure to connect you with the right experts within Canonical to discuss with you. And these are the references for some of the visualizations and some of the statistics that I've cited throughout this presentation. I hope. Okay, let me see. I'm just going to see if there are any questions that I want to answer. And that would be it for us today. Thank you, everybody, for your time. Reach out through the contact form, Jehudi.
I see one question. Do you have FIPS compliance support? The answer is yes. That's one of the advantages of Ubuntu Pro. You have FIPS out of the box, and also common criteria. So that's why this is the option for production environments, especially on regulated industries.
Yeah. And the kernels, if it is a kernel that is FIPS certified, and if that's the kernel that's being used for the confidential VM, then you effectively have to have a FIPS compliance kernel for your confidential VM as well. That was a good question. I'm going to share with you the results of the poll I launched, which is, do you require sensitive regulated data for your AI? And it is a unanimous 100%. People who are doing AI, they know they will need at some point to leverage their security sensitive regulated data. And that's why we're talking about confidential computing today. Anything else to add, Jehudi?
I see another question. How we can get the slides? So we are going to send to the email that you use for registering, and we are also going to add it to the description to the event on BrightTalk.
Yep. Indeed. We can stop here then. Send us your further questions in the contact form. We'll get back to you. Thank you for your time. Thank you, Jehudi, for joining.
Thank you.
Cheers, bye.